over the past 15 years, prior to joining UT, I was designing skyscrapers in Chicago. And then when I joined UT, I started Soft Boundaries. Soft Boundaries, a multidisciplinary research lab investigating the intersection of architecture, engineering, and sciences. And tonight, I'm very excited to present our latest work on exploratory methods in design. Our current research focuses on the development of high-performance integrated construction systems using digital fabrication, novel materials, and advanced computational design method, and robotic fabrication. So what really drove all this is that I love birds. I watch them, I sketch them, and I also learn from them. We can learn so much about birds, and we can learn from them, especially about the efficiency of their body structures. The bird's body is designed for optimal strength to weight ratio to ensure the efficient use of material. These performance goals are similar to a lot of the biomimetic principles we use in our lab. So the image on the left is actually a scan of a starling skull, the bird that we see in the United States. And also the one on the left, on the right side, this is actually an image of a topology optimized model in our lab. So the whole goal of that, the whole research was based on that our current conventional construction systems contribute to a significant amount of waste in the United States and around the world. Just in 2015 was almost over a half million tons of waste was generated. The majority of our conventional construction systems, they're considered subtractive, which means they require removal, material, trimming, milling in order to have a final part, which hasn't changed in the past 140 years. In contrast, if we look at newer technologies, such as additive manufacturing, or 3D printing is based on additive layer by layer with a waste-free processing, allowing the generation of complex geometries directly from digital models. This is a short time lapse of 15 hours of one of the research projects that I led. That's actually the reason why I joined UT, which is called AMI, or Additive Manufacturing Integrated Energy. The project proved that you can have a polymer-based additive manufacturing application in large-scale building applications. The project itself was the idea of to have a high-performance enclosure that's 3D printed with a very complex geometries, and the final prototype was designed to be paired with also 3D printed car, which was a collaboration with Oak Ridge National Lab, UT, and Skidmore, Owings & Merrill, which the firm I used to work for in Chicago. And the idea is that both the car and the building can share energy together. The photovoltaic panels on the top of the roof can actually give energy to the car. So my research in our lab now is focusing on topology optimization, which is a computational form finding. It's a process to find the best possible forms based on the optimal material distribution in relationship to load and support in combination. This is an example of a topologically optimized a prototype. We call it the U-house, which the idea follows the same principle we found in the bird's bone structure, which the idea is that reducing the amount of material while increasing the stiffness. This is the comparison on the left, which shows the normal standard framing, 16-inch on center, as opposed to the topology optimized model. Obviously, none of these will be available or make sense to start to produce this complex geometry without 3D printing. The optimized panel, this is extracted from the house, showed 34% material reduction with higher stiffness than the traditional framing structure that we normally know. Compared to standard housing. So not only this, we using material that's actually made of construction wood waste. So it's a PLA material that is enforced with fibers that's from bamboo and wood that usually would end up in landfill, but that's actually what can make a fully 3D printable parts. We are currently developing a new, more complex algorithm that's actually allowing to have a three-dimensional topology optimization, and it uses a numerical determining the material distribution in 3D space in volume. It is remarkable to see how the optimized model resembles the organic forms of the natural bone structure of the bird or the starling skull that we saw in earlier slides. This is because based on Wolff's law, this follows the same exact principle that drives the weight of reduction of the bird skeleton structure, which allows with higher stress or higher density where the maximum load is happening. So finally, this is a diagram that shows the process or the workflow, that seamless workflow with only one computational robotic fabrication that can take, we consider this research as the first step for a novel, fully integrated fabrication approach to construction driven by material economy, which hopefully have the potential to transform the current construction systems. This, similar to design principles, also apply to different scale. This is actually an example of ergonomic super lightweight chair design, where the actual principal stress is based on the human body weight. This is, we're currently fabricating this in our lab. And one of our latest projects, which has happened a couple of years ago for obvious reasons, that to combat the shortage in the personal protective supplement for gear for professionals, we actually developed and designed 3D printed face shield that also was optimized, that was only weighed 2 ounces, and we call it the UT shield. And then the face shield was donated to healthcare workers throughout the pandemic. And then last year, we collaborated with Udai, the Oak Ridge National Laboratory Governor Chair for Composites, to produce 50,000 of these in less than 2 weeks. So the work in our lab is trying to address the challenges that faces the designers striving to create sustainable built environment, and how can we have the least impact on the environment and while promoting new approach to resiliency. Thank you very much.